What's up, guys? It's Mr. Bringle, and today I'm going to be going over the impulse and force case study concept builder on the physicsclassroom.com. So for this one, you only have to do the master level. You do not have to do wizard, so it's just 4 questions here. But this is some really good thinking through momentum and impulse and force and how they're all related. So this problem states that there are 2 collisions of a PE student with the wall. In the first collision, case A, which is this one here, a 75 kilogram student moves at 8 meters per second. He collides with an unpadded wall and stops. In case B, the only difference is that the wall is padded. So same mass, same velocity, but the padding on the wall stops him. So the first thing it asks us is which variable is different for these 2 cases. Well, obviously the one with the padded wall, that is going to, just like any of our safety equipment that we talk about in class, like helmets or the airbag in a car, it's going to increase the impact time. So if you just hit the plain wall, it's going to stop you quick, versus you hit the padded wall, there's a little bit of give to it, so it's going to increase the time that it takes for that collision. Now it says, which case involves the greatest momentum change? They both have the same momentum change, right? They both start at 8 meters per second and have the same mass, and they both end at 0 meters per second. So their change in momentum is the same for each. Now it says, which case involves the greatest impulse? Well, remember that impulse is equal to change in momentum. That's that impulse momentum theorem. So if those 2 things are equal, and we just said that they had the same momentum change, that must mean that they each have the same impulse as well. Now, this one asks, the last one asks, which one involves the greatest force? Well, we got to think about this. Remember, their change in momentum is the same, but let's rewrite this equation here, and let's do F delta T for impulse is equal to change in momentum. Well, if the change in momentum is the same for each of them, but the time is increased for case B, so I'll write B down here. The time is increased for case B. For this number over here to stay the same, that means that the force of impact that case B feels must go down. So it's basically, what that means is that case A, where the person hits the unpadded wall, will have the greatest force acting on him. Once again, this is how all of our safety equipment works, is increasing the time of impact, which effectively decreases the force that you feel from the impact. Let's go ahead and check our answer. And dead away. All right, we'll go ahead and get rid of this, and we will move on to the next problem. The next problem states that there's a sad ball and a happy ball. The sad ball collides with the floor moving at 2 meters per second and stops. Okay, so it goes from 2 meters per second to 0 meters per second. In fact, I'm going to write that here. 2 meters per second, 0 meters per second. And the happy ball with the same mass collides with the floor moving initially at 2 meters per second, just like before. But then it rebounds upward at 1 meter per second. And remember, velocity has direction, so this is really -1 meter per second. That's probably the thing that will trip most people up in this problem. So it says, which variable is different for these 2 cases? It does state up here, one thing I forgot, is that the collision time is the same for each. Okay, so when going through these, there's the change in velocity. It just told us the time of the collision is the same for each. It told us the mass is the same for each. So it's got to be the change in velocity, which makes sense because this one goes from 2 to 0 and this one goes from 2 to -1. So now it says, which one has the greatest momentum change? Well, remember that momentum is equal to mass times the velocity of the object. Or the change in momentum is equal to the change in velocity times the mass. Well, most people that get this wrong will say that case A has the greater momentum change, because a lot of people will just assume that the change in velocity for case A is 2 meters per second and the change for case B is 1 meter per second, because they don't put this negative sign in here. But if you go from 2 to -1, your change in momentum for case B is actually 3 meters per second versus case A, which is 2 meters per second. So the greatest momentum change has to be case B, because the change in velocity is greater. So this is the factor right here, the change in velocity. All right, now it says which case involves the greatest impulse. Well, remember that change in momentum is equal to impulse. So if we just said that case B has a greater change in momentum, then it must also have a greater impulse, right? And then which case involves the greatest force? Let's again take this equation and rewrite it here as change in momentum is equal to force times change in time. Well, the problem told us that the change in time for the problem here stays the same. So nothing happens to that. So then the question is, how do we tell the force? Well, we said that B has a greater momentum change. So for B, this number is increased for B. Well, if the impact time was the same for both cases, then the only way that B has a greater change in momentum here is if the force of impact were increased for object B. And that should make sense because it rebounded in the opposite direction, right? So we'll go ahead and plug in B here. We'll check our answer, and there we go. Okay, moving on. This example says that there's a 600 milliliter water balloon moving at 8 meters per second. It's caught and brought to a stop. And then we've got a 150 milliliter water balloon moving at 8 meters per second, and it's caught with the same exact technique and brought to a stop. And it says the collision time is the same for each. So basically the change in velocity will be the same for each. They both start at 8 meters per second. They end at 0. The collision time is the same for each. So the difference here is in the mass of the water balloons. So we'll go through these and choose mass. Now it says, which case involves the greatest momentum change? Well, we keep going back to these equations. Change in momentum is equal to mass times change in velocity. Well, if they both have the same velocity, but case A has a greater mass, then that means that case A will have a greater change in momentum. It's harder to stop this one, case A, because it has 600 milliliters of water in it versus 150 milliliters of water in it. So greatest momentum change goes to case A. For greatest impulse, again, remember, change in momentum is equal to impulse. So if A has a greater change in momentum, then A also has a greater impulse. Now, which case involves the greatest force? Once again, we're going to change this equation to change in momentum is equal to force times the impact time. Well, it told us that the collision time is the same for each of them, so this has to stay the same. But we already identified that A has a greater momentum change, which means that the force of impact for A must be greater for this equation to hold true, since the time stays the same. The value for the time stays the same. The only way that A could get a greater change in momentum would be an increased force here. That is referring to the force of impact. Check our answer. That away. All right, the last one here. This one says that we are going to compare the collision time between two baseballs and a catcher's mitt. In case A, the baseball is pitched at 40 meters per second, collides with the catcher's mitt, and is brought to a stop. says the catcher holds the mitt rigidly and retracts backward very little as the ball strikes the mitt. In case B, an identical baseball pitched at 40 meters per second, which is the same velocity as case A, hits the mitt and is brought to a stop. However, this time, the catcher holds the mitt with a relaxed arm and retracts backwards 30 centimeters as the ball strikes the mitt. So, when we're looking through what's different here, they don't have a different change in velocity, right? They both start at 40 meters per second. They both end at 0 meters per second. However, the collision time for the two is different. In case A, the ball is caught by the mitt and the mitt doesn't move at all, right? It just hits and stops. But in case B, the catcher moves the mitt backwards and essentially increases the time that the ball is impacting the mitt, right, before it stops moving. So, think about this like if you were trying to catch a baseball with your bare hand. If you just held your hand straight out and someone threw a baseball, and you caught it without moving your hand, that's going to hurt. But if you try to catch the ball and move your hand backwards while you're catching it, it's not going to hurt you as much because you're increasing that time of impact, which is decreasing the force that you're feeling from the ball. It's distributing that force over a greater period of time. Okay, so which case involves the greatest momentum change? Well, change in momentum is equal to mass times change in velocity, and the baseballs have the same mass and they have the same change in velocity, which means that the momentum change must be the same for both. And for the next question, which case involves the greatest impulse? Remember that change in momentum is equal to impulse. So if they both have the same change in momentum, then they both have the same impulse. Now, which case involves the greatest force? Remember that impulse and change in momentum, since they're equal, we can go ahead and write it like we have been. Change in momentum is equal to the impact force times the time of impact. Well, because the time is different here, for case B, the time is increased. But we know that they have the same momentum change here. So that number doesn't change. So in order for B to keep the same change in momentum, the force of impact must be decreased for B. And that's what I was talking about at the beginning. When you move that mitt back and increase the time that the ball is impacting the mitt, then you are effectively reducing the force that is felt by the catcher's hand when he catches the ball. Versus the case A, where he just keeps it still, there's a very small impact time and a very large force felt by the catcher. So we'll go ahead and plug in A for the greatest force here. Check our answer, and we nailed it. So that would be your concept builder for the case studies of impulse and force. Hopefully that helps make a little bit more sense, and you can move on to the next one.